Hello. Today we will talk about these exotic objects called compact stars. As their name implies, compact stars are stars of some sort, but not the stars that you and I are used to going out, looking at the sky and seeing those bright objects. They are special, and as we go through this lecture, we will see how they are special. They are compact, which means they are much smaller than the stars that we see in the sky, and we will also see the reason why they are compact. But before we try to understand compact stars, let us recall some basic facts about regular stars. What are stars? Stars, as we know it, are self-gravitating globes of gas supported by thermal pressure. So, let us take a globe of gas as you see on the screen, and these inward arrows indicate that the mass of the star is causing the mass of the star is causing a gravitational force to pull the matter inwards towards the center. Unless there is an opposing force, this gravitational force will tend to squeeze the object to nothing, to a point. But matter always tries to find an opposite force, and in case of regular stars that we see in the sky, this opposing force comes from thermal pressure of hot gas that the material contains. So, material inside the stars are hot, and this hot gas, just like steam in your pressure cooker, produces an outward pressure, and this outward pressure then opposes the gravitational force and then finds an equilibrium. And when there is an equilibrium, we have a stable object, and that is the star that we normally see. Now, we see these stars, right. So, we see these stars because there is radiation coming from these hot objects towards us. So, where does this radiation come from? It comes from the energy that is contained within the star, and that energy is the thermal energy. So, the thermal energy, which is also being used to generate the pressure that is holding the star up, is being lost in radiation. So, as the thermal energy is lost in radiation, you need to replenish this thermal energy for stability to continue. This replenishment comes for the stars that we see. Our closest star is the sun, for example. The star replenishes the loss of energy from its surface by generating energy in the interior in the form of nuclear fusion. So, it is the nuclear fusion then provides the balance between the radiation being lost from the surface, which is what you see here, and the energy being generated in the interior, which is in the central part of the star, which is carrying out the nuclear fusion. So, the heat generated by the nuclear fusion then heats up the material in the star, and some of that heat is lost from the surface, and when the rate of heat generation at the center and the rate of radiation loss at the surface becomes equal, you have a stable configuration. And most stars that we see are in that kind of configuration, and the star like the sun is burning hydrogen to form helium at the interior. Nuclear fusion, as you would have learnt, creates gamma ray photons. These gamma ray photons then escape from the core, interact with the material which is surrounding the core, which we call the envelope, and through this interaction these gamma ray photons get degraded into optical light, and by the time the photons leave the surface, most of them have been degraded to optical lights, and that is why the stars we see are very bright in optical. To describe the equilibrium of these stars, we use a set of equations called the equation of hydrostatic equilibrium. In full general relativity, the equation as expressed in terms of the pressure, the radius, the mass is and the density is shown on the top. This is called the Tolman-Oppenheimer-Volkoff equation, where on the left hand side you see the pressure gradient equaling G is the Newton's gravitational constant, m here is the mass contained within the radius r, p is the pressure at radius r, rho is the density at radius r, and c, as you see here, is the speed of light. Now, this equation tells you the balance between the gravity and the internal pressure. If the object happens to be fairly large, in the sense the compactness happens to be small, or if the value of mass over radius, as we see here, the value of mass over radius, if that is small, then this equation can be approximated to the equation written here, where the pressure gradient is just gravitational constant times the mass within a radius r, the density at radius r divided by square of the radius. This quantity m, mass within a radius r, is as shown here, is integral from center to the radius r 4 pi r squared, the density at radius r times dr. So, this gives you the equation of stellar hydrostatic equilibrium, but just by itself this equation cannot be solved. You have to supply it a relation between the pressure which appears on the left hand side and density which appears on the right hand side, and once you supply that, then the equation becomes system of equations becomes closed and you can solve it. So, this equation, which is the equation relating pressure and density, is called an equation of state, and we supplement these equations with an equation of state to obtain the stellar structure. What happens through the life of a star? In the beginning, the stars start their lives as homogeneous mixtures of gas, of which about nearly 3/4 is hydrogen, about 1/4 is helium, and a small amount of material is composed of heavier elements. Now, nuclear fusion occurs in the core, where the material is hottest. In the gas globe that the star is, the surface temperature is much lower than the central temperature, and it is the temperature gradient from center to the surface that allows the heat to escape from the interior to the outside. So, the interior is the hottest, the center is the hottest, and the region around the center, which is hot enough to start nuclear fusion, is where the nuclear burning begins. This region, which is marked in red over here, is called the core. A star typically spends most of its life burning hydrogen in the core, where in effect 4 protons through several intermediate stages come together to form a helium nucleus, as you can see here. So, now let us look at the core. we have the center of the star where hydrogen is burning into helium. There are outer regions, which is envelope here. There is no nuclear fusion going on there. So, in the core, we started with 75% hydrogen and 25% helium, but now more and more hydrogen is being converted to helium. So, therefore, the composition of the core is going to change with time. Eventually, there will be no hydrogen left in the core. Once the hydrogen in the core is exhausted and the burning then can no longer proceed because the fuel is exhausted, the core then stops generating energy. Now, remember, the star was stable because the energy being lost from the surface in the form of radiation was being balanced by the energy that is being supplied from the core in the form of nuclear burning. Now, with the nuclear burning gone, the central source of energy dries up. As the central source of energy dries up, the equilibrium is now disturbed. So, in the core there is no more energy supply, but there is energy lost from the surface. So, the star begins to contract, particularly the core begins to contract rapidly under the influence of gravity. When a globe of gas contracts due to gravity, its gravitational binding energy rises. So, gravitational binding energy is a negative quantity, so the magnitude of the gravitational binding energy rises. Now, we have a theorem called the virial theorem, which relates the thermal energy in a quasi static bound object with the gravitational binding energy, which is as given here. That is, thermal energy is half of the gravitational binding energy. Now, as the gravitational binding energy rises, this actually leads to the net thermal energy also rising. 50% of the rise in the gravitational binding energy goes into thermal energy, and other 50% is lost in radiation. As the gravitational contraction proceeds, the gas actually gets hotter. So, this is an interesting cycle to keep in mind in case of gravitationally bound objects, where loss of thermal energy leads to contraction, which leads to further heating in the interior. So, as you take energy away from the configuration gets hotter. So, sometimes this is referred to as the configuration having a negative specific heat. As the gravitational binding energy rises with contraction, the material gets hotter, and while the core here is now inert, it is not burning anything. As it contracts, it gets hotter. So, therefore, the material surrounding it also gets hotter. The material surrounding it just before the contraction began was not hot enough to burn hydrogen. As the core contracts, temperature rises everywhere, and the material surrounding the core, just around the core, now becomes hot enough to start hydrogen burning. So, now we are left with a core which is not burning anything and contracting. Just surrounding it, there is a shell which is burning hydrogen, and this hydrogen burning now starts producing a lot of energy. The star becomes bright and it in fact expands, driving it to something called a red giant phase, and the core begins to continues to contract. As it continues to contract, it will continue to get hotter. If the contraction proceeds long enough, then the core temperature will rise sufficiently to ignite helium in the core. Remember, the core had already converted its hydrogen into helium. Now, it is just pure helium, and as it is contracting, it is getting hotter, and once the temperature rises to above about 100 million Kelvin, you begin to get these triple alpha reactions, where 3 helium nuclei combine to produce carbon nuclei. This process produces a lot of energy, and the core now is back with energy generation again. The core will expand, the shell sources will weaken, the overall star will contract a little, and it will get brighter. As long as the helium continues to burn, you will have a stable structure again, just like when the hydrogen was burning at the core. However, just like the first phase, the helium will also get exhausted at some point. So, as the core helium exhausts, then it would trigger the next stage of core collapse. So, just like first hydrogen, then helium with an intermediate passage of core collapse, the alternating stages of core contraction and core ignition can continue, creating heavier and heavier elements in the center of the star. But it cannot continue indefinitely, and the reason is easy to see in the nuclear binding energy diagram. So, as you can see here, what is plotted in this diagram, on the horizontal axis is the atomic number, and the vertical axis shows the binding energy per nucleon. Going from hydrogen to helium, you can see a large amount of binding energy is released. So, once protons are combined into a helium nucleus, that is a huge exothermic reaction, and this is what powers most of the star's life. The next stage of burning takes helium to carbon, which is also exothermic, and subsequently one can take carbon to oxygen, oxygen to neon, neon to magnesium, magnesium to silicon, and then finally to iron. And in fact, iron, cobalt, nickel, they are almost very similar. They stay nearly at the same place in the energy diagram, and they are called iron peak nuclei. So, up to that point, the nuclear fusion continues to be exothermic, but if you look at the binding energy curve carefully, you would see that after iron, the curve is sloping down over here, which means beyond iron, if you try to fuse nuclei, then that would become a endothermic reaction. That is no good in trying to support a star. So, in the stellar interior, various stages of nuclear burning will continue until iron is produced at the core. So, once iron is produced at the core, there will be no further nuclear fusion. The production of iron in the core will of course have come through these various stages of nuclear burning, and as we saw in the case of helium burning, there was a shell of hydrogen around it, which became active when the helium core was collapsing. Similarly, when you go through all these stages of nuclear burning, a shell of each stage will remain surrounding the core. So, just surrounding the iron core, there will be a shell of silicon burning. So, the silicon burning shell is converting silicon to iron, and that iron is going to be added to the core, and the core is going to grow in mass, because more and more ash from the silicon burning shell is added to the core. Just outside silicon, there is neon burning, which is producing silicon, and then oxygen burning producing neon, and outside of that carbon burning producing oxygen, outside of that helium producing carbon, finally outermost burning shell is hydrogen producing helium. All of this occupies a substantial fraction of the core, and outside of that there is still the envelope which is not burning anything, which contains most of the mass of the star. All of these stages of nuclear burning are possible, but not in all stars. There are processes which can halt and disrupt this progression midway, and that role is played by what we know as electron degeneracy pressure. So, let us spend a moment trying to understand what is electron degeneracy pressure. When a core is contracting, the gas in the core is getting denser. Now, as matter gets denser, electrons in this material, remember this is all hot ionized plasma. So, the electrons gets squeezed together more. Now, electrons tends to resist being squeezed together, and that is because of Pauli's exclusion principle. So, as you try to squeeze electrons together, it leads to a rise in their momentum. A rough estimate can be made in the following way. Let us consider the electron number density, which is, let us write it as n sub e. At a given electron number density n sub e, we can apportion on an average a volume per electron, which is about 1 over n of e. A volume of size 1 over n of e is like electron being confined to within a linear dimension, which is n e to the power of minus 1/3. By uncertainty principle, if you try to confine an electron within a distance like this, then it would pick up a momentum which we call the Fermi momentum, which is h cross times n e to the power of 1/3. So, that is momentum times the linear dimension equal to h cross. So, once you have a momentum, it of course has an associated energy, which we call the Fermi energy. In the full relativistic terms, the Fermi energy can be written as E f is equal to square root of p f squared c squared plus m squared c 4. This rise in momentum generates a pressure P, which is equal to the momentum flux, which is equal to the product of the number density of the electrons times the velocity of the electrons times the momentum itself. So, using that, we can try to estimate what is the pressure that this simple squeezing of electrons is going to give rise to. This quantity velocity which is present here, for velocities that are not relativistic, that means when the velocities are small, then we can write the velocity simply as momentum divided by mass. The velocity itself is p f over m e. So, now if you try to do this product, you have number density is n e, velocity is proportional to p f, momentum is proportional to p f. So, you have n e times p f square, so your pressure is proportional to n e times p f squared, and p f being proportional to n e to the power of 1/3, this whole product works out to be proportional to n e to the power of 5/3, and this is for low values of p f. So, that is low values of n e. As n e rises, which means as p f rises, p f over m, which is the velocity, which will also keep rising, but it cannot rise indefinitely. As the velocity approaches the speed of light, the velocity cannot rise anymore. So, when p f becomes very high, which happens when the number density will go very high, when p f becomes very high, then velocity will saturate at speed of light. So, the pressure now is going to have a number density which is Ne, velocity which is c, and momentum which is Ne to the power of 1/3. So, the whole product, instead of being Ne to the power of 5/3, now it becomes Ne to the power of 4/3. The pressure that is generated by the electrons by virtue of being squeezed together can then be written as the mass density to the power of 5/3 at low density and mass density to the power 4/3 at high density, where mass density is related to the electron number density by counting the electrons as a mass density divided by a quantity mu, which is called mean molecular weight per electron, times m p, which means if there are mu nucleons per electron, then most of the mass comes also from the nucleons and not from the electron. So, the total mass density of matter is number density of nucleons times the mass of nucleons. So, mass of nucleons is m p, and if there are mu number of nucleons per electron, then the number density of nucleons is mu times Ne, where Ne is the number density of electrons. Mass density is mu times Ne times m p. So, Ne therefore can be written as rho divided by mu e m p. So, if you take that density and then you can then write the degeneracy pressure, as I have said before, as density to the power of 5/3 at low density, density to the power of 4/3 at high density. And this pressure is what we call degeneracy pressure. This pressure is present even at 0 temperature, and we call matter to be degenerate when the Fermi energy EF here is much larger than the thermal kinetic energy per particle, which can be expressed through this relation, that is T f, which is called Fermi temperature, which is defined to be the Fermi energy divided by Boltzmann constant, to be much greater than the local temperature of the medium. If this is true, then the dominant pressure source is this degeneracy pressure and not the thermal pressure. Now, how does this degeneracy pressure affect the structure and evolution of stars? So, in this figure we try to illustrate the role that electron degeneracy pressure plays in controlling the fate of the stages of nuclear burning. What we plot here is a set of evolutionary tracks for two different stars. One is a lower mass star, which is the lower track, a star of 1 solar mass, and one a heavier star of 7 solar mass, which is shown in the upper track. What is plotted on the horizontal axis is the central density in grams per cubic centimeter, logarithm of it, and what is plotted in vertical axis is the log of central temperature in degrees Kelvin. As we already discussed, the star starts with a certain value of central density and temperature, where hydrogen burning is going on, and once the hydrogen is exhausted, the core will begin to contract. As the core contracts, its density will rise, and as we also mentioned, as a consequence of virial theorem, temperature will rise as well. So, the star will follow these diagonal trajectories up in this diagram. So, this track starts from here and gets denser and hotter and moves to the right and upwards. As it gets denser and denser and hotter, at some point the condition becomes suitable enough to start burning helium. And in fact, this dotted line here shows the conditions that are required for helium ignition. Now, there is a other solid line that is shown here, which demonstrates where the matter becomes strongly degenerate. So, matter is weakly degenerate on the left side of the diagram and strongly degenerate on the right side of the diagram. Remember, the core was continuing to contract because the thermal energy, which was providing support against gravity, was continuing to leak out, and as it leaked out and not getting replenished by nuclear burning, the core was continuing to collapse. However, if the matter in the core becomes degenerate, then degeneracy pressure begins to add a significant component of the support against gravity. So, if the material becomes very strongly degenerate, let us say T over T f very small, less than a percent or so, then the thermal pressure becomes actually irrelevant, and degeneracy pressure then starts providing the support and holds the collapse. If the collapse is held, then there is no further rise in temperature. If there is no further rise in temperature, a nuclear burning stage, unless it has already been initiated, will not be entered again. Degeneracy pressure support can therefore regulate how many stages of nuclear burning a star can go through in its core. This is what I illustrate here schematically as a degeneracy limited nuclear burning. The stellar hydrostatic equilibrium, as we have said in the Newtonian case, is described by this equation dP dr is minus g m rho over r squared. We can write this approximately as the central pressure equal to the gravitational constant times 2/3 power of the total mass of the star and 4/3 power of the average density of the star. In a diagram where I plot logarithm of density in the horizontal axis and logarithm of pressure in the vertical axis, this pressure support condition will follow these slanted 4/3 slope lines, and as the coefficient has m to the power of 2/3 in it, the lines will keep moving up as you increase the mass. So, this lowest line here is for a lower mass, and then a little higher mass, then a little higher mass, then a little higher mass, these sloping dashed lines. In blue is shown here the degeneracy pressure condition that we already discussed. The degeneracy pressure condition is pressure proportional to density to the power of 5/3 at lower densities, and it changes to density to the power of 4/3 at higher densities. So, this sloping line has a slope at this point parallel to these sloping dashed lines, which give you the pressure balance condition for equilibrium. But below that this line has a slope which is steeper than these pressure balance conditions. Now, let us take any of these stellar configurations. Let us take this mass. Now, this mass, as it contracts, its density will rise, its pressure will rise, and the pressure balance condition for equilibrium, as indicated by this line, will intersect the blue line at a point which is here. So, that point then fulfills the pressure balance condition, and therefore, that represents a solution which provides stellar equilibrium, which means the core, which starts to the lower left of the diagram and continues to follow a line like this for constant mass, it will keep moving up this line, and once it touches this crossing point, its collapse will stop. As its collapse stops, the rise in temperature will also stop, and therefore, the configuration will be stable there and not get into any further nuclear burning stage. Now, in red here I have indicated schematically the pressure temperature combination which corresponds to the ignition of various nuclear burning stages. So, this red line is for hydrogen, that one is for helium, and this one is for carbon. Now, consider this mass M2 here. It starts with it starts as a gas globe before it becomes a star, which contracts under gravity, and at some point it reaches this value of temperature. Once it reaches that value of temperature, then hydrogen ignites and you get the birth of a star. This ignition of hydrogen then provides the replenishment of the energy that is being lost from the surface, and as long as the hydrogen keeps burning, the star is stable at this point. Once the hydrogen burning is exhausted in the core, then the star will proceed along this line all over again. After getting somewhat more dense, the line then intersects the electron degeneracy pressure blue line over here. So, once it does so, it then finds a lasting peace over there without any further contraction. So, therefore, this star will undergo hydrogen burning, but it would not proceed as far as this to ignite helium in its center. So, a star like that will first burn hydrogen, and then before it can burn helium, its core contraction will be halted by electron degeneracy pressure, and it will end its life, the core will end its life as a globe of helium which has been produced in this nuclear fusion, and it will stay there forever with helium composition, a globe of helium composition held up by the electron degeneracy pressure within that configuration. However, if you started with a star which is of somewhat higher mass, let us take M3, before the contraction gets halted by degeneracy pressure, it will go through hydrogen burning, it will go through helium burning over here, and then before it ignites carbon, it can stop its collapse over here, and it will end its life as a globe of gas consisting of carbon and held up by electron degeneracy pressure. Similarly, if you go to higher masses, you will go through more stages of nuclear burning before being halted by degeneracy pressure. The number of stages of nuclear burning a star can go through is therefore limited by the role of degeneracy pressure, and as we can see, the higher the mass of the star, the larger the number of stages of nuclear burning it will go through. But of course, the maximum number of stages of nuclear burning it can go through is going up to the iron peak element. Beyond that, at the stellar center, there will be no further nuclear burning. Now, what happens to the configurations where the core contraction was actually halted by the degeneracy pressure? Now, it has no need of thermal pressure or heat to balance gravity. The electron degeneracy pressure provides a long lasting support. That support does not go away, cooling does not do anything to it. So, it will remain stable forever, unless you alter its mass by adding something from outside. So, these objects where you have configurations which are held by electron degeneracy pressure are called white dwarfs. These white dwarfs constitute one variety of compact stars. So, the white dwarfs is a family of compact stars. Here we have long term stability of the star without energy generation, as pressure source is not thermal. So, compact stars as a family we will define as stars which have long term support against gravity without thermal pressure, and white dwarf is one example of it. And they are compact because for the electron degeneracy pressure to be sufficient to stop gravitational collapse, you have to squeeze the electrons really hard. So, the white dwarf densities are high, about million grams per cubic centimeter. Typically, it is like the mass of the sun squeezed into an earth sized volume. So, what does the star do? We are talking about the core, which undergoes this contraction and produces the white dwarf. So, once the core contraction is halted by electron degeneracy, the matter just around the core is still burning a shell source, and this shell source is producing energy. Core is not contracting anymore. The energy deposited by the shell source goes towards gradually expelling the envelope that is around the core, and you then get into a situation like this, where you have a white dwarf at the center, and what you see around it is the matter that once used to be the envelope of that star has now been expelled to form a spherical shell around it. So, this is a very well known object in the sky called the Ring Nebula, and this picture is taken by the Hubble telescope. So, this matter, which was the envelope of this star, has now been expelled and expanded quite a bit. At the center, the core has collapsed to form a dense compact star called a white dwarf, and the radiation from this white dwarf is now exciting this star, and this star is emitting, because it is excited and ionized by the radiation coming from the white dwarf. The envelope material is excited and ionized by the white dwarf, and that radiation gives you this beautiful ring nebula. So, such objects are often referred to as planetary nebulae, and this is what happens at the end of the stellar evolution. You have the core of the star contracting and finally stopping its contraction in the form of a white dwarf, and the envelope being expelled in the form of a planetary nebula. Clearly, since the stage at which the contraction stops depends on the mass of the core, as I explained in the previous slide, you have the composition of the white dwarf decided by the mass of the white dwarf. If the mass of the white dwarf happens to be less than about 0.45 times the mass of the sun, then the white dwarf would be composed only of helium. If the mass exceeds it, then it is able to undergo one more stage of nuclear burning. So, helium burns into carbon and some amount of oxygen. So, if the mass is between, the core mass is between 0.45 to 1.25 times the mass of the sun, you are left with a white dwarf of composition which is a mixture of carbon and oxygen. If you go even higher, above 1.25 solar mass, the core would have gone through a stage of carbon burning already, and you get a composition which is a mixture of oxygen, neon and magnesium. And this is for white dwarf masses, so the core masses in the range 1.25 to 1.4 times the mass of the sun. What happens if you go even higher? Above 1.4 times the mass of the sun, no white dwarf is possible, and this is a famous limit called the Chandrasekhar limit. We will try to explain the origin of this limit. To explain the origin of this limit schematically, let us go back to the schematic diagram I drew a little while ago, where I am plotting the electron degeneracy pressure in this log of pressure versus log of density diagram. So, you have log density over here and log pressure over there. The requirement for stellar equilibrium, again as I showed before, from the hydrostatic equilibrium we can approximately write the central pressure to be equal to the gravitational constant times 2/3 the power of mass of the star times 4/3 power of the average density of the star. So, those are drawn in these various white lines over here for different values of core mass, mass increasing upwards. Where this line intersects the degeneracy pressure, blue line, you have an equilibrium solution. So, you have this mass where this equilibrium condition intersects the degeneracy pressure line over here, and you have a white dwarf solution for which the central density will be given by this value. If you have a higher mass, then the intersection point moves here, you have higher central density and so on. So, as you keep moving to higher and higher masses, you see that the central density will keep moving up. As the central density keeps moving up, you will go over from the non-relativistic rho to the power of 5/3 region to relativistic rho to the power of 4/3 regime of the electron degeneracy pressure. Now, let us see what happens if you reach a mass where the slope of this line is actually the same as the slope of this rho to the power of 4/3 line of the electron degeneracy pressure at very high density. So, this then requires that a solution be obtained when there is an intersection between this line and the electron degeneracy pressure line. So, you get to a point where these two lines just touch each other. Now, you can go to a mass which is even higher, where the requirement will now go above this maximum line that you can reach. So, for a mass like this, electron degeneracy pressure actually is not able to provide any stable solution, because there is no intersection between this line, this blue line, and this white line above it. So, this line, which is the tangent to the blue line over here, provides the maximum possible value of mass which degeneracy pressure can hold, and that is the limiting mass of a white dwarf. And this was worked out first by Chandrasekhar, and this is why this is known as the Chandrasekhar limit. Here I reproduce a figure from Chandrasekhar's own work in 1931 and again in 1935, where he plots the mass of a white dwarf on the horizontal axis and radius of a white dwarf on the vertical axis. Both these are normalized units. The mass is normalized to a number called m3. The expression of this is given here. First thing to note is that the radius of a white dwarf becomes smaller when the mass increases. This is opposite of what our normal experience is with matter of familiar kind. In terrestrial conditions, you take an iron ball and you take a heavier iron ball. The heavier iron ball is bigger in size than the lighter iron ball, whereas in case of a white dwarf, a heavier white dwarf is smaller in size than a lighter white dwarf. So, as the mass of the white dwarf increases, it gets smaller and smaller. The density in the center rises dramatically. And what Chandrasekhar draws in these diagrams, in shaded portion are the portion of the white dwarf where the material is relativistic, that is Fermi energy is larger than the rest energy of the electrons. So, initially for white dwarfs which are less massive in upper branch of this diagram, the relativistic core is imperceptible, but as you go to the heavier white dwarfs which are more dense, the portion of the core which is relativistic grows, and eventually by the time you reach the end of this curve, the entire white dwarf has become relativistic. And as this shows that because at that point there is no further support possible, the radius actually goes to 0. So, this limiting value of the mass can be computed exactly from the white dwarf Fermi gas equation of state. So, if you just take electron degeneracy pressure, the full expression of the pressure is shown here. This is not just in two asymptotic regimes which we did before, but this is the complete expression going for all densities. The quantity x here is the ratio of Fermi momentum to electron mass times the speed of light. You take this equation of state and use the stellar equilibrium equations. In this case, one is using Newtonian gravity, which is dp dr minus gm by r square. Then you get to this expression for maximum mass, which is now shown here, which is a number constant times h c over g. H is Planck's constant, c is speed of light, g is gravitational constant to the power of 3 halves times 1 over mu e, which is the mean molecular weight, times proton mass squared. This quantity is called the Chandrasekhar limit. It is important to see that the Chandrasekhar limiting mass is expressed in terms only of fundamental constants and nothing else. Numerically, this then works out to be 5.75 solar mass divided by mu e squared. So, mu e, as I said, is the mean molecular weight, which is number of nucleons per electron. Now, we have already seen what kind of composition white dwarfs have. They are either helium or carbon oxygen or oxygen neon magnesium. In all these cases, there are roughly equal number of protons and neutrons, which means for every electron there are 2 nucleons. So, mu e is 2 for almost all of these cases. So, once you put mu e equal to 2 in this expression, you get a value which is 1.44 times the mass of the sun, which is the well known Chandrasekhar limit.